So indeed, my name is Jakob Löhnertz. I was born and raised in the Rheingau region of Germany, next to Frankfurt, who won UEFA Europa League yesterday. And I moved about 4 years ago here to Amsterdam, originally to study a master's degree, but then I liked it very much, so I stayed ever since. I'm actually a Java software engineer at Picnic, the online supermarket, actually quite close by from here, our headquarters. We actually, in the backend at least, sadly do not even use Kotlin, of course, for our Android app, unsurprisingly. But yeah, maybe someday would be nice. Yeah, Java I'm using daily, which is also a fine language. But today, of course, we're talking about Kotlin. What I'm doing, I'm actually running an educational YouTube channel. It's a bit quiet, sadly, recently, because there's a lot of other things I have to do. But I'm on a new video that will release soon. And there's also quite some Kotlin content. You can see the name here on the left-hand side, which is also where the slide template is from. Where I'm actually using Kotlin pretty much for everything is various hobby projects, personal projects. I'm into all things remote controlled, mainly cars and multi-copters, watching very large variety of different sports. And myself, I'm practicing bouldering, snooker, and darts. Right. Enough about myself. You're here for Kotlin. And we're today going to talk about the compiler, Kotlin's compiler. So if you have something like this here, right? Simple Kotlin code. We have a sealed interface. For those of you who don't know, in a nutshell, it's a regular interface, as you would know from other languages. However, at compile time already, it's clear which implementations there will be of this interface. So you'll see which it allows for is that we can do something like here on the left-hand side with this when statement, where we can say, is my random sealed instance, is it A, is it B, or is it C? And of course, typically in a when statement, you always need an else case, right? Because yeah, there is always an else. In this case, and that's the feature of the sealing, the Kotlin compiler knows, due to the fact that the interface is sealed, the only implementation that there's going to be is A, B, and C. So it actually tells us that you don't need an else case, which is one of the few examples. And then I wondered, after seeing features like this and many others that make Kotlin really nice, how the hell is this like implemented to run on the JVM? Because obviously there's no sealed interface in Java, and JVM bytecode is pretty similar to Java, of course. And secondly, how do they like enforce that this even works in the way that the Kotlin feature is supposed to work, right? So yeah, welcome to my talk Dekompiled, where we're going to be analyzing how Kotlin's features are represented on the Java virtual machine, JVM for short. Right. So what we're going to do today, let's first start with an introduction to the topic, just so I don't lose anyone from the get-go. It's going to be quick and basic because you don't need much more, but a bit of intro is good. Then we're going to look at how Kotlin's features are represented on the JVM. So how do we get something like the sealing in JVM bytecode? And finally, we're going to look at how Kotlin's compiler enforces that these features, such as the sealing, actually do what they're supposed to do, and you don't end up with a regular interface, which is what you don't want in this case. Right. So let's start with the intro. Kotlin's compiler. It's this blue box right here. In this example, it's called Kotlin C, analogous to Java C, I guess. So if we have our Kotlin source code here and we shove it in from the left-hand side, the first step, as many other compilers also have, is a front end. So this is where we would parse apart the Kotlin code into a more abstract representation, and we do some analysis. So that means stuff like, okay, this method wants an integer that you don't pass a string, stuff like this that you can statically check and so on, and all sorts of analysis that makes sure that, well, the language sort of specification is respected. Then the next step is the middle end. So what that means, this is was actually not originally a Kotlin compiler, but is in there. Well, it was in there, but not in the way it's nowadays. But it's in there for quite some time by now, which is where we convert our Kotlin code that we parse apart into what's called an intermediate representation, or IR for short. What is that? So you abstract away a bit and move up to a more generic representation, more intermediate one of Kotlin, because of course Kotlin is very Java-esque, right? That's known to us. And the problem would be, of course, since one of the big killer features of Kotlin is that you can compile into a variety of target platforms, if the compiler for various target platforms every time would have to implement all the way from Kotlin, which is close to Java, to, let's say, JavaScript or native code or something, which is very not like Java, it would be having to do a lot of heavy lifting every time. So instead, the compiler designers decided to first go to intermediate representation, so the step to the final platform is a bit shorter. And what happens here as well is that we do some IR-based optimization. So this is just typical things you would know from compilers, like, I don't know, it figures out certain cases in your conditionals are not even used, or they're always true, or whatever, and it optimizes them away, or like unwraps a loop or something like that. But regardless of the target platform. And then the final step, unsurprisingly, is the backend, where, of course, the big thing is we do actual code generation. So this is depending on the target platform, and this is the most common ones, although, of course, there's more actually common. You actually convert it to JavaScript or JVM Bytecode or JVM Bytecode, also known as a native target. And the other thing we do here is some more specific optimization to that target platform. So JVM Bytecode, for instance, has very different data types than JavaScript, for instance. So you can do some optimization that might work very well on V8 for JavaScript, but maybe has a detrimental effect actually for JVM target. So that's where we optimize a bit further for that specific target platform. And then at the end pops out our code or whatever it may be for the target. Today we're only going to focus on JVM Bytecode because firstly, this is the most common platform, of course, due to Android alone already, and I presume it's also the one that you have the most experience with in the audience. Right. So JVM compilation. Let's quickly run through it as well. Of course, the thing that Sun and Oracle and OpenJDK are advertising all the time is that JVM is so portable, right? And this is, of course, indeed the case. So you can, from various source languages, can compile into JVM bytecode. Java, Kotlin, Scala, there's also Groovy and Clojure, and many smaller ones. And they can all compile to the same JVM target bytecode, with the nicety of a side effect that once we have the bytecode, we don't even know anymore, like, was this once Java, was this once Kotlin? Of course, there's like a bit of things we can tell by, which is partially what you'll see in this presentation today. But you get what I'm saying. It doesn't matter too much anymore. And that's also, of course, where we get interoperability from, right? That we can do something like calling Kotlin code from Java and vice versa. And actually in the latest Scala version, they also added interoperability, which is what would be very hard if you would, I don't know, call Python from Kotlin or something. Works, but pretty tedious. And then, of course, finally, we have our bytecode and we run it on our actual virtual machine. That's quite straightforward, I guess. So what I wondered then is something like this ceiling with the interface that you saw at the beginning. A, how does this work? And B, how do all the other Kotlin features actually work? So what I did is I analyzed virtually all Kotlin features I could think of. Here's actually the full list of them, and try to figure out how are they represented when running on the JVM. Right, before we look into this, last quick excerpt into JVM bytecode. Don't worry, this is all you'll see of it, and you also don't need any prior knowledge, and I'm also by no means a big expert on this, but this is what this would look like. Although it's actually not, of course, quite what it would look like, because it's a binary format. If you ever open a .class file in a regular text editor, it's a bit of garbage. But most JVM implementations ship with a small tooling that you can convert a class file back into this human readable format. And as you see, if you've never seen bytecode before, it's based on instructions, and it's a bit like getting closer to, of course, lower level to something like an assembly language. It's still a lot higher level, since we can do stuff here like 27 throw in exceptions and something that you would know from Java. And in any case, the important bit here is of course, it is very, very close in terms of its methodologies and so on to how Java works, unsurprisingly, given that it's Java virtual machine bytecode. However, the problem is now, of course, this is pretty tedious to read. You can get a hang of it. Like, it's okay for something like this, a simple two-string method. It's okay to read, but it's still very tedious. And for something here for talk, it's very boring as well to look at. So what did I do instead? I did this methodology, so to say. So I created for each of the features that you saw earlier in this cloud, I created a small snippet. Super stupid code. It doesn't do anything properly, but an example for each that purely does what I wanted to see in that feature. And I just compiled it with Kotlin C into JVM bytecode. And what I figured then is, and tried out a bit, is that there's decompilers, of course. So you can take JVM bytecode and figure out again what was the original Java code that came into it. In this case, I used CFR. There's others. I figured this one works best for Kotlin, or originating bytecode, let's say. Because, of course, the decompiler, A, doesn't care, and B, also doesn't even know that it decompiles bytecode that actually was never Java, right? It's meant mainly for Java decompiling. So, for instance, use case would be reverse engineering is a common one, of course, and maybe even restoring code where you lost the source code. I'm not sure, it happens sometimes, I guess. Or, of course, like today, for educational purposes. And then I found that even though, of course, JVM bytecode is lower level and it's not Java, the two are very, very related, of course. So it is actually pretty feasible, apart from very few features, to do this step here, this methodology, and look at the resulting Java code to figure out how the Kotlin compiler, enforces and represents its features when running on the JVM. And well, Java is quite easy to read, specifically if you have some prior knowledge to Kotlin, right? The only feature actually that doesn't work very well is the suspend keyword. There's so much magic going on. It's the decompiler gives up pretty much. But for the others, you can very clearly see how this would look and work. One warning: these decompilers are not perfect, none of them, because well, that's not really a use case that should exist, right? So they have to do some guessing work in there. So sometimes the output code in Java is super noisy and has like a lot of stuff that you wouldn't expect in there, and it, for instance, casts everything into everything all the time because of type erasure. I cleaned it up a bit already in these examples, but it's quite clear anyways. Right, let's move on to actually the topic of the talk. How are the features represented on the JVM? Right, so this is actually how this would be represented in the case of the ceiling. So this is the output Java if you would run it through this pipeline I showed you. So you see actually the interface is an interface. It's just a public interface called sealed. Then we have this one implementation here. You actually see here also how the object keyword in Java, in Kotlin works. It does, unsurprisingly, what you would do in Java with a singleton. So private constructor and just one instance of this class. And then on the left-hand side, you see how the when statement turned out. So it's just converted to an if-else statement and uses instance of to do this is checking. And then you see actually that it synthetically, so to say, inserted the else case for us here. So there's an else case that it throws a custom no when branch matched exception, which wasn't even there in Kotlin, of course. For the case, and we'll see that a bit later, where there are ways, of course, that you can like circumvent the ceiling. It still has to insert this because there can be cases that there is actually a fourth D implementation, and then of course you need this else case. However, in Kotlin, of course, the ceiling you want to have in a way that ABC, that's it. So let's figure out how this can work. So in general, the compiler has two major options that you saw earlier from the pipeline to represent the features. First would be the front end. So if we think about something like nullability, for instance, the way that it works in Kotlin is, of course, that the front end has to do a big part of the work. So you have a method that accepts a non-nullable type. You want that if I pass null, the compiler front end screams at you, and it doesn't even continue going to the backend, right? That's the whole point of the non-nullable types. And this is the case with many other things as well. So these are things you can sort of statically check and that you can enforce before it even gets to the later stages, where you start doing any sort of code generation. And then the other option is the backend, or in some cases actually the middle end as well to an extent, where you want to represent things that can be represented in JVM bytecode, but might be very tedious to do. So to give an example, the in keyword, where you do like a loop. So you say for I in 1 to 10 or something. What it obviously will result in is a regular for loop at the end. So you just want to have that in Kotlin. It looks very nice and syntax sugary and so on, that it for I in 1 to 10 looks very good. But then, of course, in JVM bytecode, since no one sees that, it will just like unwrap that into a regular for loop with incrementing the I every time. So you will find that all obviously of the features from this cloud earlier use one or the other. Most will actually use backend features of the compiler, so they can be represented and there's not really any hacks or something necessary. In bytecode, it's just that it's a lot uglier than it would look in Kotlin. You'll also find that some of them actually use both. So something like the nullability or actually the ceiling as well will use both. So you have a front-end part where you need to do some checking. Hey, is this is this actually non-nullable type that you gave me here? But you also actually have a backend component because it will compile in that if for some reason there is a null passed in, for instance, if you call it from Java, that at least it immediately throws an exception and it fails fast, right? So this uses both. And you saw in the ceiling case as well. Of course, it wants to check, hey, is the ceiling actually respected? And you see it compiled in the synthetic else case, which wasn't even there in Kotlin. So this example also uses both. Right. Let's move on to the second point, how the features are enforced on the JVM. So if you look at what we saw, how this is like converted into bytecode or Java in this case, it's this. But this is not a sealed interface, right? It's just an interface. So how is it possible that when you then use this, for instance, in a library, that it can still figure out, okay, this is a sealed interface? Because the information seems to be lost. What you need for this extra information is this bit. So there's this annotation, metadata, and this is what we're going to focus on now. So what the Kotlin compiler will do is that every single class it compiles, it will add this metadata annotation on top. You can also not stop it from doing that. And as the name implies, it contains metadata about whatever follows in this class. MV, metadata version, is just the compiler version. K and XI we don't care too much about. The interesting ones are D1 and D2, which is data 1 and data 2. You see in data 2, there's sort of identifiers and pointers to what data 1 is about. And you see data 1 is not even human readable. So in here we see apparently something in data 1 points to this sealed interface. And we do something with the getRandom method and so on. And it will contain metadata, and we'll see in a moment what, to enforce the features. We're not going to look into too much, actually in no detail, what exactly is in there, because A, as you can see, it's not readable, and B, this completely differs per feature that it sort of points to. So depending which class this sits on, the format and so on in D1 is entirely different every time. Right, but this is important information to have. Cool, now consider this case. We have a Kotlin library that we use from somewhere, Maven Central, I don't know, that's distributed as a jar. Sometimes, of course, developers will add their source sets, so you still have access to the original Kotlin code, but it's not required. For some libraries, they don't add that for, I don't know, whatever reason, or specifically older ones also oftentimes don't have that. What we will only have then in this case is a jar which contains the bytecode, right? With these metadata annotations. And the thing, if you think about it now, is there's no way to even knowing anymore that this was once Kotlin code, right? It's just JVM bytecode. There's no notion anymore that this was originally a Kotlin library. Of course, you will have the README and it says here's a Kotlin library. But if you think about it from the raw bytecode that you actually use in your application, yeah, there's no notion of Kotlin anymore. So then, how is it possible if we take first the top part of these branches, if you then use this library, you call a method on it, for instance, or you use a sealed interface from it, in your own Kotlin code, in your own application, how is it possible for something like the ceiling and the nullability and so on to still be sort of respected for front end and back end of the compiler? And you might have guessed already, the answer, of course, is this metadata annotation. So what the compiler will do if you have this library on your class path and you compile it, it first, of course, will read the bytecode and to do things that you don't need any metadata for. For instance, again, example, do data types match? Something like, again, I have a method that needs an integer, you cannot pass a string into it. That you can purely check with just the compiler. But then anything else that is not purely representable in the bytecode, such as the nullability, to stay with that example, would then be read out of the metadata. So the compiler would figure out, oh, this and this method is non-nullable, the type is non-nullable, such that if you then compile and you pass a null, it'll actually blow up, which without the metadata, if you think about it, impossible, because there's no, in JVM bytecode, everything is nullable. There's no non-nullable types in Java, so that is not even an option, apart from primitives, of course. Same with the ceiling, as you saw. There's no sealed interface, it's just an interface. So without this metadata, it would be impossible to still have this feature when using a library where you only have the bytecode. Right. On the Java side of things, so this would mean you call this library from your Java application, which works, of course, is a bit worse, obviously. The nice thing, and this is why it's so nice the way the Kotlin compiler developers pulled this off, the nice thing about the metadata, or these annotations, of course, is in JVM bytecode that they're entirely optional. So the The Java compiler will be just like, well, there is this annotation here, but I have no idea what metadata is supposed to be, so I'm just going to ignore it. So it will still read the bytecode, so you get what is like in the JVM language specification, obviously. So again, data types match and so on. But you will not get any of the other features of Kotlin, such that you can, of course, if you have a method that expects a non-nullable string, for instance, you can pass a null into it and it will not stop you from it, and actually will just blow up at runtime because the compiler doesn't even know what is non-nullable types. So that's, of course, where it falls short a bit, but yeah, that's Java's fault, not Kotlin's. So that you would get something like this, right? And think about it, this is only possible due to this metadata annotation. If you have a library here where we get a random, this is complete bullshit code, but if you get a random string, without the metadata annotation, the compiler wouldn't even be able to say, okay, this is a string and not a string question mark. Because if you lose these metadata annotation for some reason, it has to assume, well, everything is nullable. So you get what you get in Java if you use a library there. Everything is question mark at the end. Or you can leave them off, I know, and it sort of hopes that it's not nullable. But by default, it will say, yeah, this is Java library. It has to be nullable. And then, of course, you get what you see in the third line. If we then combine nullable and non-nullable type, the compiler again will scream at us, this is not allowed in a collection that's just non-nullable strings. Right. There's a slight twist to this if you use IntelliJ, where it's a bit nicer actually than just with the compiler. Same example, exact same example. This time, of course, we want to sort of get this. And you of course noticed already, I guess, this is a screenshot out of IntelliJ. So what we want, and this is what makes IntelliJ using it so nice, together with the Kotlin plugin, unsurprisingly, given that both Kotlin and IntelliJ are from the same company, that yeah, the user experience is very nice in the sense that you oftentimes don't even need the compiler, right? This you can get without even starting Kotlin C once. It'll squiggly line, as everyone of you knows, and you can see before getting to the compilation phase, it tells you, yeah, you can compile it, but I can already tell you now this won't work. And unsurprisingly, the Kotlin plugin in IntelliJ also uses this metadata, of course. It has to do actually pretty much very many steps that the compiler also has to do at the end, because of course it has to figure out, read the metadata, do some checking, do the types match, and so on. So very heavy lifting, of course. But you get this right here. On the Java side of things, this is actually a bit improved now. So what it will there do is it will still read the bytecode, but also these generic annotations that you might have seen before. I'm sorry, I hope this is readable. Well, more or less. I'm sure you've seen this before. So what the Kotlin compiler will also do, it will not only add these metadata annotations everywhere, it will also add more generic ones that can be used by any sort of tooling. So you see here, my constructor here has this not null annotation from org.jetbrains.annotations package that it adds everywhere. There's also a few of these others that are for like very large scale features, not something for like sealing, but some like nullability that's like very integral to Kotlin. And then what the IntelliJ plugin will do for Java is it can at least read these annotations, right? And still you can then get the same result right here. So if you then would use a Kotlin library and you pass null into it and it doesn't expect that, it'll actually in IntelliJ tell you this won't work. Of course you can still compile it, right? Because then the Java compiler again is like, everything's nullable, I don't care. And it will again blow up at runtime, which is actually why there's a bit of or quite a large actually value proposition that IntelliJ can give you that not even the Java compiler can give you. So these kind of, this class of bugs, let's say, you can spot or you can catch very nicely with IntelliJ that with pure compilation you wouldn't catch. Yes. One note about these metadata annotations, they can take quite a lot of space, of course. They're added to each and every class that you compile. So if you have a large application, this can actually add up quite some space in terms of kilobytes. What you can do, and what is fairly popular in the Android world, is to strip this out afterwards. So if you think about it, if you have an APK on the Play Store that you want to distribute, no one will call the code on that anymore. So the metadata annotations are useless. They're just sitting around. No one will ever read them, and it's not really necessary. So what people do, there's custom tools. There's nothing that the compiler will do. They will just you compile your classes, and then before you bundle the APK, you sort of strip out all the metadata annotation, which can shrink the APK quite a lot, of course. Which, yeah, sometimes is really nice if you make the download faster for the user. So if this is something that you're worried about, also for distributing any other sort of Kotlin code, actually look into that, because they can add up quite a lot. Right. So this was the theoretical side of things. Let's move to a practical part. So you saw all these features earlier, right? And so we want to go through how some of them are represented. So I prepared, this is a selection I did, mainly because I think these are one of the more interesting ones, and B, because I prepared slides for them. So go ahead and scan the QR code if this is big enough, or go to the website here and vote for them. And then until I run out of time, we'll just go through the top most voted ones, and I'll show you how this is represented and enforced, as you've learned now. While we wait for a few seconds, if we can do like one question, I figured, since if there's one.
Yeah, does anyone have any questions already that we could pass on to Jakob while we wait for the voting?
If not, I'm also around all day. So
he just explained everything too well, Jakob. That's the problem.
Yes, I hope so. All right. I'm not going to put it up on the screen, but anyways, you see it on your phones and you got to trust me. Apparently named argument. Let's give it a few more seconds. Very close. Yeah, there's 3 top runners. Let's see if we can get through them. Right. Let's start with named argument. Named argument is actually one of the funniest ones. So that's good. I'm sorry, this is so small. There we go. Right. Named arguments. So what are named arguments? Just quickly, if you don't know, you see here we in our method we pass in query and then we pass in start, right? But of course, what we can do in Kotlin, which other languages also have, but importantly Java doesn't have. In this case, we flip it around. So we say start is true and query is Kotlin, which is not the order that the method expected it as. And another thing you'll see here is that I also use a default argument for the Boolean. So yeah, you see this is like swapped around. Interestingly, the way this is represented is very easy. And when I saw it, I was like, okay, this is a bit almost too easy. Actually, what the Kotlin compiler will just do in this case, it just swaps it around. So you see it's at the bottom part here, you see the method. So it's first the string and then the Boolean. And then the top it's called. And you see it literally just will go there and sort it in the way that the method expects it, ignoring whatever custom sorting you gave it. So this is a very clever idea, of course, but almost a bit too simple, I guess. And the other thing you actually see here as well is how the default argument is done. It looks a bit funky, but the second method you see is has this $default in it. And you see that we only need the string. Ignore a bit these other weird things it passes. The Boolean and the N are only used to sort of hard code that the Boolean is false in this case, as I did. And the object actually here at the end is only used sort of to make sure that there's no overloading clashes. So it just adds this object that is not used for anything and passes null actually in this case when you call it. Just to make sure that not accidentally there's some clash because you had the exact same method name or some stuff like that. And then you see the Boolean is hard-coded to false in all cases, and we still then call our other method. Actually, pretty simple solution. Another thing you see here very quickly is something that the decompiler will add. So you see sometimes add this synthetic here. So what this simply means is it's actually pretty interesting to know about. There are things, and the else case in the beginning from the ceiling was actually an example like this as well, where you have something in the bytecode that was not there at all in your Kotlin code from the beginning, right? So you see here the default method we didn't declare. We just said, okay, this is default. So this is a very good example again of compiler backend, right? So in Kotlin looks really clean, really nice. You say just equals false, that's my default. And then in bytecode it generates this whole ugly looking extra method. But you'll never see it, right? That's the beauty of it. And that's why it adds synthetic here, because it didn't exist in the original code. And you also see that's a synthetic main method, actually, because in Java, as you know, I guess, you need this dreaded public static void main string array args, which in Kotlin you don't. And you see what it just does. It compiles in a synthetic main for that, and then we just call our custom one without any arguments. So same idea. Right. Reified keyword, that's a good one because I think that's one of the very most interesting ones. Where is it? Here we go. Right. So what is reifying? Just quick summary as well. How are you doing on the time, by the way? Okay, that's good. Reifying. So you have something like this here. We have I made an extension function called supertypes. All these examples are very stupid, so don't think too much about what they do. But they want to, of course, I want to showcase the Kotlin feature, not the code. So it's an extension function that will give you the supertypes of a generic, of a parameterized type, anything. And this is also not possible in Java, of course, because due to type erasure, you cannot do something here that you get a T, so the parameterized type, and you say, what's the class of this? And that's possible with reflection, of course, but not in the language. There's no way to do that. And this is where you need the reification. So you see here, we say our T is reified, which means that at runtime, the Kotlin runtime can still, or the JVM can still figure out, access what is actually the T that was passed in here. And the other very important thing that you have to note here, which if you ever use reification, you'll also know that, is that we have to add this inline keyword. The IntelliJ, if you use reification, will actually tell you add the inline keyword, otherwise it won't compile. Again, a good example of a front-end feature, because the front-end will check, is there inline keyword? If no, I cannot even do the feature. And you'll see now why that is. So this is represented in the following way. Quite simple again, actually. All of these are pretty simple if you think about it, but clever as well the way they pulled it off. What it will do is it will just, for every single call side of this extension function, it'll just hard code the type that was called with there. And that's of course also why we need the inlining. So inlining, if you're not aware, is that you move, copy paste, so to say, the whole method body into the call side. So you see here the method at the bottom actually is not even called. This is completely unused. This is purely there to actually, I'm not even sure why it compiles it in there. The interesting bit is the second line in the main method, which you see it just took what we actually called in the end with our class.supertypes thing, and inlined it there. And then you see in this case we call it with what we receive from the main method, the string array. So it will hard code there, string array. This information here is not lost, and it's hard coded at that specific place. So what it will actually do is, if you use this at 50 different times, it'll always just copy the whole method and hard code whatever at that call site you called it with, to be able to retain the type information. Very, very clever idea, but yeah, figured that was quite nice. Right, let's do one last one, which is the inline keyword, apparently. Where is that? I still have an old MacBook with like a weird, what is it called, touch bar? Here we go. This is the only time I ever used this. Right, inline. We already touched upon it, what it is. So this simply means, as I said, that you, mainly for performance reasons, want to move a method body into the call side. Main reason is to not add a stack, a frame to your call stack every time. This is mainly used for methods that are very that either you call super often or that are so generic that that you would have to add call stacks everywhere. A good example of this, where you might have used this before, is all the scope functions. So you have something here like the apply or also, and all of these are inline functions in the Kotlin standard library. So you see here the important bit to look at is at the right side it says public inline fun, right? So what will happen then simply is that what it's supposed to do is it should take, instead of calling also with the lambda and whatnot, it should just copy paste it into the call side. And this actually is, again, a very simple one, unsurprisingly. It'll just do that. It'll just take, and this looks very ugly due to this, it'll just take the entire function and sort of takes your lambda and will just like push it one indentation further to the left and sort of just calls it there. And the whole lambda actually is also gone. This is, again, very nice because A, you don't need to allocate the lambda object in the heap, and B, you don't add the frame to the call stack. So this is good old just imperative code at the end. You completely lose the lambda is completely lost actually here. Again, this is probably the prime example of where in Kotlin it looks very nice and you have the lambdas and it looks pretty and very, very nice syntax sugar. And then if you look at this here, it's like very ugly and not so nice. But this is exactly, of course, what you want the compiler for. Kotlin looks nice, and then all the ugliness, the reality, so to say, that you have to run this on the JVM, you hide away behind the compiler, and you never have to look at this apart from this talk. Right. I think we're almost out of time, so let's wrap it up. I have something for you still, though. So we only saw 3 now, and there is actually over 40 in this word cloud earlier. So what I did is all the others that you didn't see, and including those, obviously, I put all of them on a public repository on GitHub. So what you'll find there is always the Kotlin snippet and then the decompiled Java. So you don't even have to look at the bytecode, although of course you can do that if you want to. I recommend checking it out. It's pretty interesting to see how some of the other ones end up. As I said, most will have backend components to represent them. And second most often is that it actually uses both. And purely front-end usage in the compiler is actually pretty rare. Right. Let's wrap it up with that. If you want to stay in touch, this is my Twitter account. Go ahead and follow me. There's also the link to the YouTube channel. I would, of course, appreciate if you check it out. There's quite some Kotlin content there. And apart from that, thank you very much for your attention, and I hope I see you around today still.
Thank you, Jakob. Good job. We do still have time for 1 or 2 questions if anyone out there has any. There, right there, front row. Here we go. Thank you, Ellis.
Hi. I wonder how the inline works backwards, where you read a Java file and how Kotlin figures out that this is an inline and how it does inline it. Right.
I'm not 100% sure, but I would presume actually that it sort of just ignores that it's just because at runtime you don't really need the inlining. Sorry, at compile time you're not really interested in the inlining aspect because there's nothing that IntelliJ would need to show you that you need to do or something. So I would presume I'm not like the answers. I don't know, but I would presume that it sort of will just use the bytecode and just compile your stuff on top of it essentially because there's nothing really before the compiler that the inlining aspect is important for. So in this case, I think that's fine.
Great. Any other questions? Oh, we've got a few. All right, nice.
Hi.
Hey.
Do you think there's a big cost in Kotlin? Because it does add a lot of extra stuff on top of the JVM basic features.
I mean, there are, if you want to check that specifically, do you mean cost in terms of runtime performance? Or?
Yeah.
Yeah. So, I mean, there are benchmarks with here, what is it called? The microharness thing from JVM to benchmark it. And it doesn't make it a lot slower because most of the thing that it actually adds there are purely used in the compilation phase. So at runtime, these annotations, for instance, they're there. Of course, it increases the size of whatever you distribute it via, but at runtime, they're completely ignored. And actually, some of these tricks that you saw, such as the inlining or so, of course, are there to improve the performance. So I think in most cases, at least the benchmarks that I've seen, no, it doesn't make it any slower really. And of course, you can make a lot of tweaks in the compiler that to reach pretty much the same performance that Java compiled bytecode would have. So not really.
Thanks.